is Özgür Bezgin. He is joining us from Istanbul University, and I'm not gonna, is it Cerrahpaşa? Cerrahpaşa. Well, thank you for joining us. He's going to be presenting on the uses of the Bezgin-Kolukirik equations to estimate the highest values of dynamic impact forces due to wheel flats. So, welcome.
Thank you. Hello. My name is Özgür Bezgin. I'm attending from Istanbul University Cerrahpaşa, and today I will be presenting to you our work, which I did with my graduate student Bezgin-Kolukirik, where he and I developed an equation together using a methodology that I presented earlier to estimate the highest values of dynamic impact forces due to wheel flats. Now, as we all know, wheel flats are a major source of service and safety disruption along railway tracks. And my university, together with SNCF, we collaborated in a project called CMED, where the highest values of the dynamic impact forces due to wheel flats can be investigated both numerically and analytically. Now, I realize that I'm one of the two remaining presenters that is between your lunch, and so I'll try to make this as enjoyable as possible, because listening to all these beautiful presentations about both experimental studies, a variety of sensor technologies, as well as wonderful numerical analysis methods, I learned a lot. Now today I'm going to approach this from a different perspective. My motive actually for beginning this project altogether was my understanding that the engineer should be able to propose a solution to a pressing engineering problem manually by using a paper and a pencil. Today's actually problems require advanced technologies to evaluate. I agree with that, and we need that. But I also think that we need to have an analytical perspective to the mechanical problems that we are facing. So the method which I introduced in the year 2017 in St. Petersburg, Russia, is a method developed analytically to estimate the highest values of dynamic impact forces due to track roughness and wheel roughness. Today I'll be talking about wheel roughness. And the method bases on the law of conservation of energy, rules of kinematics, and the newly introduced concept of impact reduction factor. Now, I won't have time to go into all the details because they have been studied and presented and also introduced to railway engineering literature beginning from 2017 all the way up to 2021. So if you're interested, you're more than welcome to refer to those resources. I'm going to provide some of the final results that we attained from these studies. Now, the variations in track profile and track stiffness along the rough length of track would be our track roughness presentations. Today's discussion will be about the wheel roughness, and the fundamental analogy here is a speed bump analogy. So what does a speed bump do? It changes the potential energies of the tributary masses that compose the rolling stock. So the rate of change of this energy is actually what's causing the dynamic impact forces that we face. For the track roughness, we considered previously the variation in the track profile and track stiffness, and for the wheel flats, the momentary disruption in the circularity generates this potential energy variation. The equations that I developed with my student, Cengiz, basically relies on these concepts and estimates the highest values of the dynamic impact forces due to the wheel flats. So today I'll be discussing about these two equations, which are part of a set of 7 equations. And so we have 2 equations, one of them considering the wheel flat an original the original shape of the wheel flat, and this one includes the Hertzian contact flattening that reduces somewhat the effect of the wheel flat that has not been mechanically or plastically deformed. So the analytical methodology considers some of the let's say, deterministic aspects of the rolling stock and the track, the mass distribution of the rolling stock, the stiffness distribution of the rolling stock and the stiffness of the track, as well as the kinematics of the motion, the speed of the train, and the geometry of the track roughness, in this case the length of the wheel flat, and most importantly the diameter of the wheel that this flat has occurred on. These two equations, the first one here is at point A, we have a perfect point which actually does not exist in reality. But this K prime B3 equation is developed to estimate the dynamic impact force as this flat wheel hits the railhead. The second one actually includes this local Hertzian contact flattening that somewhat reduces the effective drop height due to the wheel flat. And again, the fundamental starting point of this whole discussion is that all the potential energies of the tributary masses carried by the wheel, including itself, and transferred at the point of contact with respect to the statically deformed track, can generate a higher deflection, C prime, that's greater than A prime, and hence this variation in the potential energy. Now, how much this C prime will be is a question of what the rate of the change of the potential energy is. So as a tribute to my hometown, the city where I grew up, I named it as the Ampere hypothesis, and it says that the vertical dynamic impact forces imparted onto the railway track by a moving train vary with the rate of change of the potential energies of the tributary masses. As again, coming from the speed bump analogy, if we go over the speed bump very slowly, nothing much happens. But if we traverse over it fast, or if the change in the profile of the surface that we are moving on is very abrupt, this change occurs abruptly and hence generates a dynamic impact force. What we see here on the left-hand side is the potential energy. This is the potential energy that is waiting to enter into our track, but a certain percentage of it is actually does not transfer into the track. So this impact reduction factor F that I mentioned earlier, we can see it over here. And I have a linear and elastic consideration for the rolling stock and the track system behavior, especially in the service conditions. This was actually, this kind of eases up the algebra, but if it's a non-linear behavior, that can also be represented by an equivalent system. So what happens here is that if this value of F is 1, nothing happens. This potential energy does not enter into the track and the static deflection remains the same. But depending on this value of H, a part of this potential energy enters into the track, causing a dynamic impact force. So at the end, we have a relation between the dynamic impact deflection with respect to the static deflection through this factor. Now this factor is instructive in the sense that it relates, explicitly correlates its value to the amount of roughness H and the representative of the system stiffness represented by A prime. The higher the system stiffness is, the lower is the A prime. And if you know one thing about the dynamic impact forces, a higher stiffness environment generates high dynamic impact forces. This also actually represents the effect of the static wheel force, meaning that all else being the same, a heavier train for a given roughness will experience a lower dynamic impact force factor. Let me stop briefly over here. If we have a very heavy train pressing onto the track so much that any minuscule variation in the profile becomes unnoticed, as opposed to a lightweight train where even a smaller disturbance in the profile can generate a higher impact. So this was basically an explicit relation. Through this, we were able to provide this explicit relationship. Again, F represents the part of the potential energy of the tributary wheel masses that is transferred into the track, and for the wheel flats, it is a ratio of the hypothetical time to fall to the time to spin, because it's an angular motion. So once we represent it kinematically, if the wheel is rolling very slow, such that the duration of time to spin is very long, F approaches 1 and no impact occurs. But as the time to spin becomes equivalent to time to fall, then F approaches to values smaller than 1, and it can even fall below 0, generating high impact values. So when we bring all this kinematic equation into this, at this point, we arrive at an equation that explicitly correlate the dynamic impact force, the highest value, the P1 forces, the so-called P1 forces, those high frequency and low duration P1 forces, because in order to have an understanding, I think, about all the damages that we see on the railway tracks and the rolling stock components, I need to understand the forces. And some literature says that, well, P1 forces are not that effective, which I disagree. They may not be as effective to go all the way down to the ballast layer, but at the real and the real contact, I think that they're effective. So this methodology is estimating P1 forces and not the P2 forces. I would like to indicate that beforehand. So the true benefit of this equation is that it explicitly correlates it to the length of the wheel flat, the speed of the train, the diameter of the wheel. I mean, again, like for example, I came up across certain specifications putting limits on wheel flats for all types of wheels, which made me think that, can we say that? I mean, if we have an infinitely sized wheel with, say, 2-inch wheel flat, will the effect of that 2-inch wheel flat will be the same if the wheel was only, let's say, 6-inch in diameter? So the curvature should have an effect, just geometrically speaking, and through this equation, we were able to portray that. But of course, I need to add here that numerical analysis, for example, also considers the contact durations. I mean, a train going at an infinite speed, for example, the point of roughness has no time to contact, right? If the velocity is infinite, then the contact duration is 0, hence then there's no time for the force to convey into the track. So numerical analysis is, that's why we use it. But in this analytical approach, the assumption is that the contact durations are sufficient to convey all the forces into the track. The track has time to understand that it's the track and that it is being loaded by these impact forces. But again, contact durations, especially at certain levels, at high levels compared to the stiffness of the system, has an effect in what percentage of the forces actually has time to generate. But in this approach, the contact duration is assumed to be sufficient for the forces to develop. So let me introduce some of the results, for example, that we conducted for the two wheel sets, 920 millimeter and 720 millimeter, where we compared the two wheels. And I put them to the same scale to show that the blue lines are actually the estimates that disregard the Hertzian contact deformation. So if we have a 5 millimeter long, 0.2 inch long wheel flat, we see its effect. That's not the case because the Hertzian contact deformation will actually kind of just get rid of its effect. But the point I'm trying to make here is that, as you can see with the wheel flats, it's not perfectly linear, by the way. It appears so, but it's not. It is lower. So for the lower wheel, the smaller wheel, we have a higher dynamic impact occurring for a given wheel flat length. And these orange estimates are the effects of the wheel flat, depending on our treatment of the Hertzian contact width. The effect of a wheel flat is actually basically nullified by that flattening. So it's somewhat smaller, but the effect of that local Hertzian contact diminishes as the wheel flat length increases. And if we compare the two, again, the estimates for the smaller wheel is higher, dynamic impact force estimates. So which leads me to think that then how can we specify, if we were to specify certain limits on the wheel flat lengths, how considerate should we be of the wheel diameters? Because we would like to make the wheels as small as possible to carry the most load that we can carry, right? Because the idea is not the trains, it's to transport people and goods. We just need the trains in between. So we want to make things smaller as possible to make it the carry goods as much as possible, which leads me to take that, for example, Talbot. In the early days, in the beginning of the 20th century, the equations developed always had a parameter they were considering the wheel diameter. Because the question was how to make it smaller. We would like to make it smaller to have a greater volume to carry the goods, actually. If we compare the estimates for the 920 millimeter diameter wheel with respect to the 720, there's the results vary up to from about like 4.5% to somewhat 14%. So the dynamic impact force factors has a certain difference. Now, Essentia Brazo, again, this I have been presenting this in the Transportation Research Board meetings. I'm a member of the committee there, so I made my presentation. They showed interest in my work. They made their presentation. I showed interest in their work. So we decided to collaborate, and they have developed a fantastic numerical model that combines a variety of expensive numerical analytical methodologies, and they also basically analyzed certain hypothetical cases, actually not so hypothetical, these were actually actual trains and track conditions. So what we did was, unfortunately my colleagues are not here to comment more on their side of the work, but I will just introduce the pictures, and it is a very complicated numerical analysis model. It takes some time to run, of course, but it is a very useful model. So what we did was, for these given conditions, for the K-track, K-primary, for K-secondary, so the total works, we were able to model that and the mass distribution. For an 835-inch wheel diameter, for a 2-inch wheel flat length, we first looked into what would be the estimate, how do the estimates compare for a 56 kilonewton, roughly 30 kip wheel force, static wheel force, and a 26.3 kip. Yeah, that should be kip. Static wheel force. And these are the comparisons. Now, of course, numerical analyses, the second black box, there are some intrinsic workings within that box that we don't know, right? I mean, too many indeterminate interaction, time iterative, simultaneous solutions are taking place. So one thing for sure is that for the higher speeds, it is taking into consideration the contact duration. And this is one of the reasons why the estimates are actually reaching a flat line, a plateau. Now the green ones are the estimates of our equations, analytical equations, and there's somewhat an agreement between 100 kilometer per hour to roughly 300 kilometer per hour practical range of service. And one thing that their model also shows is that as the static wheel forces decrease, the dynamic impact force factors increase. A lighter train will be impacted more, comparatively speaking, because any effect of the roughness will become more visible with respect to the static system deflection. So this hypothetical expectation was actually confirmed by the two approaches. And there's a better agreement for the higher static wheel force between 150 and to 300 kilometer range. Why is the numerical model behaving like this? SNCF did not comment on that either. Again, it's this numerical intrinsic workings of these equations sometimes that generate these conditions. And again, this is a comparison for the comparison for the wheel flat lengths. This one being for the 30 millimeter wheel flat length, and this one being for the 50 millimeter wheel flat length. Again, this agreement between the two results, between this service range, was shown. So this is an ongoing study, and as the results come out, we will be presenting them. But the methodology that the Bezgin method and the resulting equation have thus far shown their benefit to their beneficiaries in terms of explicitly correlating the highest values of the expected dynamic impact forces due to track and wheel roughness. With that, thank you. Thank you.
Thank you. We do have a question. Can I apply the equations to estimate the flat spot length and depth, knowing already the diameter, speed, and load of the axle?
Yes. Yes. It can be back calculated. If it's the highest dynamic impact force value estimated, it can be back calculated to what may have generated it. Yes.
Okay, that's the only question we have, but do we have any other questions in the room? Well, I just want to thank you for sharing with us too the origin of naming your hypothesis, because many times we find ourselves in rooms talking about these things 20 years from now and saying, I wonder why it's called that. So maybe someone will talk. Thank you very much for your presentation.
Thank you very much.
We have one more presenter in this